Welcome to my channel. Super Heterodyne Radio Receiver is one of the most widely used architectures for AM, FM, and other types of radio reception. It works by converting the incoming radio signal, RF, to a fixed intermediate frequency, IF, where the signal can be more easily processed and amplified. Here's a detailed breakdown of the Super Heterodyne receiver, block by block. 1. Antenna. Purpose. The antenna captures the electromagnetic waves, radio signals, from the air, which are typically transmitted in the form of amplitude-modulated, AM, or frequency-modulated, FM, waves. Function. The radio waves, RF signals, received by the antenna are typically in the range of tens of kilohertz to gigahertz, depending on the frequency band AM, FM, SW. 2. RF amplifier. Purpose. The RF amplifier amplifies the weak radio signals received by the antenna. Function. It increases the strength of the incoming radio signal to a level that can be easily processed by the rest of the circuit. This stage is necessary because the signals captured by the antenna are usually very weak. Characteristics. The RF amplifier is typically tuned to amplify signals of a specific frequency band, the FM or AM radio bands. 3. Mixer, frequency converter. Purpose. The mixer is the key component that enables the super heterodyne principle. Function. The mixer combines the amplified RF signal with a signal generated by a local oscillator or LO to produce two new frequencies, the intermediate frequency or IF, and the difference or sum of the original RF and LO frequencies. The difference frequency between the RF signal and the LO signal is the intermediate frequency or IF. This IF is easier to process and amplify, as it is usually at a fixed, predictable frequency. The mixer also produces an unwanted sum frequency, but it is filtered out in the following stages. 4. Local oscillator or LO. Purpose. The local oscillator generates a high-frequency signal that is mixed with the RF signal to produce the IF signal. Function. The local oscillator typically operates at a frequency that is either above or below the incoming radio signal by a fixed amount called the intermediate frequency. For example, in a typical AM radio receiver, the local oscillator might be 455 kHz higher than the incoming signal. Characteristics. The frequency of the LO is variable in many radios, as it is tuned to match the frequency of the incoming signal and create a stable IF. 5. IF filter. Purpose. The IF filter isolates the intermediate frequency or IF signal from the unwanted sum frequency produced by the mixer. Function. The filter allows only the IF signal to pass through, rejecting all other frequencies, including the unwanted LO and RF signals. Characteristics. The IF filter is typically a bandpass filter that only allows a narrow band of frequencies centered around the IF to pass. This filtering improves selectivity and ensures that only the desired signal remains. 6. IF amplifier. Purpose. After filtering, the IF amplifier further amplifies the intermediate frequency signal to a level suitable for demodulation. Function. The IF amplifier boosts the strength of the filtered IF signal. The advantage of amplifying the IF signal instead of the RF signal is that the IF signal is at a lower, more manageable frequency, which is easier to amplify and demodulate. 7. Demodulator. Purpose. The demodulator, also called the detector, is responsible for extracting the original audio or information signal from the modulated carrier wave. Function. Depending on the modulation scheme, AM, FM, or others, the demodulator works to recover the baseband signal. AM demodulation. In an AM receiver, the demodulator extracts the audio signal by detecting the variations in amplitude of the carrier wave. FM demodulation. In an FM receiver, the demodulator extracts the audio signal by detecting variations in frequency instead of amplitude. Characteristics. For AM, a simple envelope detector or diode detector can be used. For FM, a frequency discriminator or phase-locked loop or PLL circuit is often used. 8. Audio amplifier. Purpose. The audio amplifier amplifies the demodulated audio signal to a level that can drive speakers or headphones. Function. After the demodulated signal is extracted from the carrier, it is often weak and needs to be amplified to a level suitable for listening. The audio amplifier boosts this signal. Characteristics. This stage typically has a wide frequency response to accurately reproduce the audio frequencies. 9. Speaker output device. Purpose. The speaker converts the amplified audio signal into sound that can be heard. Function. The amplified audio signal drives the speaker to vibrate, producing sound waves corresponding to the audio information that was originally modulated onto the radio signal. 10. Tuning circuit. Purpose. The tuning circuit allows the user to select the desired radio station or frequency. Function. The tuning circuit adjusts the frequency of the local oscillator and the RF amplifier to match the frequency of the incoming signal. This enables the receiver to select a particular station and reject others. Characteristics. In older radios, the tuning circuit was typically a variable capacitor, while modern radios use digital tuning methods. Summary of the superheterodyne process. 1. Antenna. Receives the radio wave RF signal. 2. RF amplifier. Boosts the weak signal. 3. Mixer. Combines the RF signal with the local oscillator's signal to create an intermediate frequency or IF. 4. IF filter. Isolates the IF from other unwanted signals. 5. IF amplifier further amplifies the IF signal. 6. Demodulator. Extracts the original audio or information from the modulated signal. 7. Audio amplifier. Boosts the demodulated signal to a level suitable for output. 8. Speaker. Converts the audio signal into sound. Advantages of the superheterodyne receiver. Improved sensitivity. Since the IF is fixed and typically lies in a frequency range that is easy to amplify, it provides better sensitivity and selectivity than directly amplifying RF signals. Stability. Using a fixed IF makes the receiver more stable, as variations in the local oscillator frequency have less effect on the overall performance. Selectivity. The use of intermediate frequencies allows for better filtering and rejection of unwanted signals. Conclusion. The superheterodyne receiver remains the foundation of most modern radio receivers because of its ability to provide good performance in terms of selectivity, sensitivity, and stability. By converting the RF signal to an intermediate frequency, it simplifies the processing and amplification stages, making it easier to design and more efficient for practical use. I hope you enjoyed this video. Don't forget to like and subscribe. See you next time.